Thank you for joining the Once Changing the World, India's first Future Tech Meets Sustainability podcast. And today, I'm delighted and honored to have with me Mr. Auke Ijspeert, who is a professor at the École Polytechnique Fédérale de Lausanne and heads the Biorobotics Laboratory. He holds a BSc and MSc in physics from EPFL and PhD in artificial intelligence from the University of Edinburgh. His research interests lie at the intersection of robotics, computational neuroscience, nonlinear dynamical systems, and applied machine learning. He focuses on understanding animal locomotion and movement control through numerical simulations in robotics, drawing inspiration in biology for the design of novel robots and locomotion controllers. His work also explores assistive technologies for individuals with limited mobility, including exoskeletons. So, Professor, really appreciate you taking time and being part of the podcast. Creating bio-inspired robots. It would be great if you kind of like explain that, because biology itself has taken like millions of years to evolve. We have these dragonflies with some brilliant aerodynamics, and then we've got these apes, and we've got humans, with or the dexterities. It's insane, because when you talk about a bio-inspired robot, what do you actually mean by that? And are there any specific biological systems, organisms that inspire research? And will be great if you could also talk about how you incorporate these features or these inspirations into your robotic designs.
Yeah, so like you, I'm fascinated by animals, and the more I do robotics, in fact, the more I'm really impressed by how animals move, how they rarely fall, they're able to navigate very complex environments and do all kind of incredible things. And I think that the robotics perspective can be interesting, first of all, on understanding the science of animal locomotion. So that's really a scientific purpose to use robots and the robotics approach as a scientific tool to understand animal locomotion. And then the other aspect is engineering, is indeed making systems that can approximate or approach the agility of animals. And here, as you said, animals are incredibly good. They have evolved so many years to be very agile, energy efficient, robust. They can repair themselves. So here, robotics is doing very well, but we can still take a lot of inspiration to make our systems better, for instance, to locomote in very complex environments.
So when you mention about these science of animal locomotion, how do you go about learning that? And how do you go about like kind of leveraging those understanding or insights to integrate within these robotic systems?
Yeah, so here the interest is obviously to collaborate with people in neuroscience or biomechanics to together address important questions. In fact, we start having a first idea of how animals locomote and how their control systems interact with the body and the environment to do locomotion. But still, it's a very complex problem. Just the neural circuitry has multiple layers in the spinal cord, in the upper part of the brain. Very complex structures, multi-layers that are complicated. The musculoskeletal system is very complicated, has many components as well, is highly nonlinear. And of course, the environment can be very complicated. And here, I really think that the robotics perspective can be useful, because robotics and roboticists are used to see how components interact, to make systems that interact. And therefore, having a robotics perspective can be very useful to reverse engineer principles. And for instance, investigate how the spinal cord of vertebrate animals control locomotion, a topic that I find very interesting. So I think that that's a bit the idea, is the robot becomes a tool in which we can test hypotheses. We can do things on the robot that we cannot do on animal. I'll come back to that later. And I think that's very interesting, then to collaborate closely with scientists to use a robot to understand better animals.
Professor, can you give me an example of these reverse engineering, these biological traits, and then how do you integrate them into robotics?
Yeah, I can give you several examples. So first of all, in my lab, we're very much interested in vertebrate locomotion, so animals that have a spinal cord. And we're very much interested to decode going from swimming, for instance, in eels or lampreys, to swimming and walking in salamanders, which are amphibians. Also locomotion in cats. We're interested in mammals. And we're also interested in human locomotion, to understand how human locomotion works. So to give you a concrete example, for many years we have been interested in salamanders, for instance. Salamanders are incredibly interesting. They are amphibians, very old animals that can swim and walk. And it's quite impressive how they can switch between different gaits depending on the environment. And neuroscientists have found that it's really the spinal cord that does everything. So the circuits in the spinal cord are completely in charge of locomotion. And higher parts of the brain are not so much needed to do locomotion or even gait transitions. You can do that by isolating even the spinal cord of the animal, stimulating it erratically, and finding that there are very sophisticated circuits in the spinal cord. So what we have done as roboticists is made mathematical models of these spinal cord circuits, like neural network models or other type of models. And we have made robots that have a bit of morphology of salamanders. And we have been able to demonstrate that indeed, if you design the system properly, starting from a swimming circuit, you can add specific circuits to control the limbs. And with some specific ideas that are a bit technical, we were able to demonstrate that indeed a very simple input to that system, representing the descending drive to the spinal cord, could completely modulate the speed, the direction of locomotion, and even the gait, swimming or walking. So there, the robot and our models were really instrumental to show at least a principle of how it could work in the real animal.
Right. So, Professor, when you talk about these mathematical models, you create these simulations. How does this, these sim to real life translation happen? I mean, what are the problems and challenges over there?
Yeah, there are multiple challenges. So first of all is choosing the right level of abstraction, because you don't want to simulate things at the level of molecules or even at too many, like the hundreds of thousands of neurons in spinal cord. We computationally, it's very expensive and doesn't make sense to simulate everything. So often we are modeling things at a quite abstract level, like couple oscillator models, as we call them, or neural network that simulate the local circuitry of the spinal cord. So that's a bit at the neural network level. And then, interestingly, we can already explain many things. So we can explain how, if you give them more excitation, these systems start to oscillate faster, exactly like in animals. We have the hypothesis that some oscillates are slower than others. We have some hypothesis that some oscillates, like for the limbs, will saturate if you try to activate them too much. So these are all kind of insights we got through our models, and that were then validated on the real animal. And at the same time, at the same level, the biomechanics we approximated with a bit. We use quite traditional DC motors to simulate muscles. So we have motors to simulate muscles, and we have a body that's a kind of simplification of the real body, but still pretty good at simulating swimming and walking.
Can you explain central pattern generators and their significance in both animal locomotion and robotics?
So central pattern generators have been discovered more or less 100 years ago. And these are circuits, neural circuits that you find in the spinal cord. And these are circuits, neural circuits that can oscillate by themselves. You need sometimes to excite them a bit with pharmacology, with chemicals, or with electrical input. But then these are very interesting circuits that produce rhythms, like neurons starting to produce rhythms. And we see them as feed-forward controllers to the muscles. So they already provide, for instance, in the lamprey, where they have been discovered, they already provide very nice rhythms, but that even coordinated along the spinal cord to produce traveling waves. So you see an eel or a lamprey does a traveling wave. So the central pattern generator by itself can make these rhythms and have a nice phase lag to do a traveling wave. And that's like built in as a feed-forward controller in the circuitry. Of course, you have feedback on top of that, but it's a very interesting building block, very useful for many modes of locomotion.
Can you elaborate on the neural mechanisms that underlie the visually guided behavior in your salamander robot, and what insights have these studies provided in the design of these bio-inspired robots?
So some of the main insights we got is indeed how this beautiful principle, like by the way, one nice analogy to see the spinal cord and the musculoskeletal system is to see it like a puppet on string, with strings. So a finite set of strings, not too many, are sufficient to modulate very complex movements generated by the spinal cord. And that's a very interesting multi-layered control, so that the high part of the brain doesn't need to worry about every single muscle. It just worries about where should I go and with what speed. So it's really multi-layered control, and the spinal cord is in charge of doing the complex low-level things. And for instance, in some project we studied visually guided behavior. Indeed, how very simple inputs from vision could then see obstacles or specific targets. And just by playing with a few descending strings, you could activate very nicely the speed, the heading, and have the salamander follow a target or approach a target and avoid obstacles. And that's exactly how we do when we do locomotion as humans. We rarely think carefully where we should place our limbs. That's the spinal cord that does it. We just think about more or less where we should go, and we rely on the reflexes and the spinal cord to stabilize our locomotion.
Can you share updates from your biorobotics lab, and what are you currently working on? You mentioned about Lamprey, this thing, salamander, legged robots. It would be great if you could talk about what you're building at this point currently at your biorobotics laboratory.
So we have several projects that I find very exciting. So first of all, one aspect also that we work on with biologists is to try to reverse engineer evolution. So we have swimming robots like eels. We have salamander-like robots like amphibians. We have quadruped robots like cats, and in simulation mainly we do human locomotion as well. So here for each of them we have PhD students who make models, and we try to see what has changed during evolution to go from simple swimming to much more complicated cat locomotion. And one thing that we're finding out, which I find quite exciting, is the fact that the control architecture has not changed that much. Like the neural circuitry has getting a bit more sophisticated, but not that much. While the morphologies have been very different and the type of locomotion is very different. So what we're finding is that nature has somehow found a nice way of designing a control architecture that could be fairly rapidly be downloaded in a new morphology that has been explored during evolution, and therefore being able to find new modes of locomotion as well. And I like that because it could be very useful for robotics to do the same. Now, to give you some more concrete examples, we one big project we have these days is to study how sensory feedback plays a big role in locomotion. For instance, in eel-like locomotion, we have been able to demonstrate that eels, which are super robust against lesions, like you can make a cut of the spinal cord of an eel and it will keep swimming. And we have been able to demonstrate using our models that this is very much likely based on sensory feedback, compensating for missing connections. And then the robot was very instrumental. I can show you some videos because we could systematically test different types of transactions without harming animals. It's purely in the model. And we could see what happens if we activate feedback or not, or if we activate coupling or not, and be able to demonstrate that indeed by having sensory feedback, we are surprisingly robust. So robust that you could even have a swimming animal, a swimming robot that has no direct communication within any segments, and they just rely on the local feedback to have very stable locomotion. So really beautiful emergent swimming patterns relying purely on the local feedback. Something that that I think people underestimated, and we could demonstrate that.
Awesome. So you mentioned about these different types of robots, right from lamprey to salamander and eels. Professor, what would be the applications of this, and has any of these robots been taken to the industry where there's been some applications which has been useful?
Yeah, it's true that our main objectives in my lab is is a bit more fundamental and scientific, so to understand animal locomotion. And but you're right that there could be many interesting applications, especially for amphibious robots. So we had some spin-off projects where we used the robots that we designed for science to see if we make them more robust and if we equip them with sensors. We had two projects, one where we wanted to use a robot for search and rescue. Like here, we collaborate with people who work on rescue teams, and they told us a very complex situation for them is a collapsed building in a flooded area, because there's water, there's danger of the building collapsing, and this will be a situation where they will not send rescue teams, not even rescue dogs will be sent there because it's too dangerous even for the dog. So it's very problematic for them to see if they're survivors or to inspect the status of the building. And here we adapted some of our robots to be able to crawl and swim and to be remote controlled, so that you have like a remote presence and be able to inspect buildings. We were not there completely yet to make a product that's stable enough to work properly, so it was still work in progress. But this notion of having a remote controlled robot that could be crawling around, swimming, sometimes walking, switching between modes could be very interesting for inspection tasks for search and rescue. Exploring pipes or sewers or offshore platforms, so it doesn't need to be rescue, but anything that needs inspection in a complex amphibious environment could be, I think, very interesting with our robots.
Yeah, there are people such as Elon Musk and all who are saying that in the next possibly decade, there'll be like billions of robots, and it will be different kinds of robots. Like there's some people who are building humanoid robots, the legged robots, and then these amphibious robots. I'm sure the future is getting like really, really exciting as well as very scary, which obviously we're going to talk about. But we would love to talk, about your assistive robots. You've also doing research and building exoskeletons, and these assistive furniture robotics. So it will be great if you kind of maybe first explain what are these exoskeleton robots, how do they are currently being used, and also assistive furniture robotics, your robots.
Yeah. So indeed, when I present my lab, I always say we have three missions. One which is understanding locomotion, like robots for science. The other one is to engineer locomotion, so making systems like amphibious robots for search and rescue. And the third mission is exactly the one you mentioned, is using robots or robot technology to assist people who have lost mobility or have partial mobility. And here with one of my colleagues, Mohamed Bouri, he's leading an independent group called the Reassist. He's making a whole series of very interesting exoskeletons that help people who are either fully paraplegic, let's say, that really need completely assistance. And then you have the exoskeleton, so a system that you wear with motors on the knee joint, the hip joints, to be able to locomote like with the help of the exoskeleton. And he also works on making systems that can help people who have lost partial mobility. So they're just weak, and then you need to coordinate with the person. And here, the contribution of my lab to what Dr. Mohamed Bouri does is to see if we could use our models of the spinal cord that we developed of trying to explain human locomotion, try to use them in real time to be the controller of the exoskeleton. So we can have a virtual spinal cord to redo what the spinal cord should do normally for that person. It's like reflexes to correct steps when you fall, to create the patterns for locomotion. And that seems to be a very interesting approach to have quite natural gaits, especially for persons who are paraplegic. So that's one type of assistance which I find very interesting, and applying a bit what we learn on human locomotion to control these exoskeletons.
Right, and it works in assistive furniture robotics.
Yeah, so the assistive furniture robotics, that's a bit what I call my science fiction project. It's something which I find very exciting, is the idea of if you are in a wheelchair, maybe more than having a humanoid robot assisting you, what could be super useful is to have the furniture around you to assist you. Because anyone needs furniture, you have friends coming over, you need a table to eat, you have a coffee table. So why not make that furniture mobile, that it can move around? And why not give it with a mobile arm, so that if you have lost a pen on the ground, why not have the table pick it up and bring it to you? And then we started doing that. So we started creating assistive furniture. So we have like 5 pieces of furniture that can move around you. And that opens the door to very interesting applications, because indeed first of all, if you're in a wheelchair and the apartment is a bit small, it would be very interesting, and that's what we did, is have furniture to go out of the way when you cross and then come back in place when you cross the apartment, just to facilitate the movement of the wheelchair. Another thing that's interesting is you're having friends over for beers or tea. Why not be able to program the room to take a specific configuration? So say, okay, now we are ready to host people. And finally, as mentioned, if you need to manipulate something or carry something with you, or if you have lost the remote control, why not have the coffee table pick it up, bring it back to you? And the interesting part here is that the assistance is there when you need, and once you don't need assistance anymore, this becomes just furniture like you need anyway. So you really embed the assistance in your surrounding. And I find that quite exciting.
Super interesting. But I think almost all the tech is like super interesting as well as scary, because what would a world look like where we become so lazy that we don't even get up and do our own work? Because I guess through the history, I think, I mean, we've been automating things or creating these mechanisms, where humans are losing their skills. I am completely pro technology, but it looks like, I mean, we're going towards a world where, like the Wall-E kind of movie, where there are these fat blobs sitting, not doing anything, waiting for they are. But I mean, yes, I mean, it would be such a game changer for those people with disability, and especially I think the aged population, because there are a lot of these aged population where there's no children home, and then they are very dependent, and these assistive furniture robotics would play such a great role over there. So yes, I think we're getting into a fantastic world, but we are also getting into a world where we are creating these tools which could possibly maybe handicap the future generation, the people who are like who want to be lazy. So this exoskeleton, it's like a very fascinating subject, because I mean, you mentioned about assisting paraplegic, people who are disabled. Obviously it also will be eventually used in militarization, because these exoskeletons would be giving you these augmenting or human strength. So do you kind of worry about that? And maybe also we will obviously talk more about the downsides of the these robotics, but just maybe your thoughts on these exoskeleton being used in military purpose, and when do you see these exoskeleton kind of available all over the world? Because I mean, even right now, I think these exoskeletons, the price points are like really, really expensive. Do you see that in this decade the price points going down, it actually becoming a tool for people with disability?
Well, you addressed here many important topics. Let me maybe address each of them, if I may. So first of all, I want to go back to the furniture, because I completely agree with you, and I always take the Wall-E example of things we should not do. We don't want to make people lazy. So that's why the assistive furniture is really meant for people who need it. So paraplegic or tetraplegic, where it's a lot of load for the family and caretakers to take care of the person. So if you could be a bit more independent and the furniture help you, I think then we need it. But otherwise, I think we should indeed be very careful not to make people lazy. And we have some ideas for that, by the way, because you could use the furniture also to exercise for both people who need it, like rehabilitation, but also for normal people. So the same thing, a motor, as you know, is both, you can use it also as a generator. So you could, either the furniture could move by itself with the motor, or you could use it as an exercising device. And in principle, you could collect and harvest the energy by reversing, using the motor as a generator. So there's a whole way of using the furniture to make you much more active. Because you could also gamify it to make it like fun game, where we have the idea of maybe making a Pac-Man game where you have to avoid the furniture or you have to dance with the furniture. So, this idea of keeping people mobile and not making them lazy and keeping people engaged and active is super important for me. So we want to avoid the Wall-E scenario, absolutely. So that's a bit to address these possible worries with assistive furniture. Now for exoskeletons, I'm really a pacifist. So I know, and I'm a bit worried when robots are used for war, and indeed a big push of exoskeletons is to make super soldiers, augmenting soldiers so that they can carry more, walk longer, etc. I don't find that exciting, and I find it a bit worrying. So I agree with that. And then in terms of the price and accessibility, Interestingly, now there's now I don't remember. There's a company making exoskeletons for helping hikers. So it's a company that sells clothes for hiking, and they now have I don't know the price, but you can buy something with a simple knee exoskeleton to help you hike better and longer. So the little by little things will become more products and more accessible, maybe in that way. Well, I'm not an expert, but I know that one thing that slows down the market is regulation. Often the technology in labs is quite advanced, but regulation makes things very slow and costly. Some companies just disappear because they cannot handle the regulation properly or get the proper rights. So that's slowing down the transfer of technology to products. Now how insurance can pay or not for this. One exciting news is that the US now very recently allowed for insurance to cover exoskeleton costs. So that will be a big boom for exoskeletons to be more affordable and covered by insurance in the US. So that is taking more time than planned, but I think it's coming.
Right.
And of course, you want to make products that are easy to use, put on and off. Maybe one mistake that labs often do is that they care about optimizing walking in a bit simple conditions, but then they forget that walking is just one activity. You want to sit up, sit down, you want to go into your car, you want to take it off and on and off very easily again. And if that doesn't work properly, people will never use the devices. So I think some devices have been too much focused on performance, but not enough on wearability and this all the other aspects that are super important. So that still needs, I think, research in academia to do that better.
I'm sure, when these exoskeletons, become market ready and it's widely available, I think the kind of impact it'll have on the people who are disabled is like really, really fantastic. While obviously, the other side of the world, which is, the nations will actually want to kind of augment the army and will obviously acquire these exoskeletons for army, and that's where I think maybe things might go wrong, because even currently today, the Ukraine Russia war, what I hear is they are widely deploying drones, and in fact Russia, the reason I think Russia is not being able to like kind of they were very arrogant about it that they would destroy Ukraine. They are not able to do is because their whole tankers failed against these drones. These cheap drones have destroyed their $1 million tankers, and now I think the entire game is changing right now. The Russians are also adapting, and they are buying more drones now. So in this race against constantly adapting to and creating these low cost technologies, which is more potential, I don't know where the future would go. And you mentioned about regulations, and I hope that there's more people who understand both the societal impact of technology as well as, people who are actually in it building technology, because there is no technology which is a good technology or a bad technology. It's always, it's when it gets into the hands of the people, how they use it, it becomes good or bad. So I think, there shouldn't be regulations, because, we should always celebrate or scientists and researchers, because people such as yourself are at the forefront of building things for us, the future. Because who would have imagined like assistive furniture robotics? That's such a superb and awesome idea if you kind of give it a thought. But yes, that's the downside of it, that these new generation who are all addicted to or digital format, and who are completely hooked onto games and are becoming lazier by the day. The attention span is going down. I'll worry about them. But yes, I'm for as least regulation as possible, and we should celebrate technologists and give them all the tools so that you can build more technology which is safer and better for all humanity. What are your thoughts on humanoid robots? Are you building humanoid robots? You mentioned you building something in the simulation. What are your thoughts on robots such as the Tesla bot, and then there's China's engine AI. There's a company there. There's a robot called SE01. I really love the way they're using the robot for the gates. The way the robot walks. What are your thoughts on humanoid robots? And is there something that you're working on at the laboratory currently?
Yeah. So the field of humanoid robotics is booming. I was recently at IROS, a big conference in Abu Dhabi. So it's one of the two big conferences in robotics in the world. The other one is ICRA, and it was also in Yokohama before. In both, if you go to the exhibition hall, one half was humanoid robots. The other was quadrupeds. So the whole field of legged robots, quadrupeds and bipeds is booming. It's incredibly active, and it's like a boom we had 15 years ago with flying drones. Now we have it with legged platforms, which I find super exciting because I'm in legged platforms. So the boom is quite impressive. So it's moving very fast, and the prices are going down. And that's exciting because that makes things much more democratic. The prices are so much down that now quadruped robots can be bought for a few $1,000s. Before it was like in the tens or even hundreds of $1,000s. So now almost any lab in the world can do quadruped robotics at least. Human robots are still a bit more expensive, but still getting cheaper. So there's a whole boom of things happening that are very, very exciting. To be honest, I think more. I see many more applications for quadruped robots on humanoid robots, or even there's a whole world there that we should not be restricted to four-legged or two-legged. There's so many combinations we can do: wheels plus legs, or six arms, or we can do many more things. So sometimes we are a bit too restricted in the design space because of our what we see in biology. We can open up this space much more, but still, it's indeed very much exciting and booming. In my own lab, we have worked on humanoid robots for quite some time. A bit less these days because we didn't have access to a good platform. So we had one that broke, in fact, and we could not use it anymore. So most of the work we have been doing was on the computational neuroscience aspect, and that was purely in simulation. So using what we call neuromechanical simulation, simulating the biomechanics, the neural networks. And that was really to see indeed how human locomotion is similar and different from other vertebrates. And there we got some interesting insights.
Right. So even the current robots, I mean, they excel in a structured environment, where you have to kind of give them like clear rules. I mean, do this, do that, but they kind of struggle with uncertainty, in complex decision making. What do you think are the challenges that lie ahead in building a fully autonomous robot that adapts to unforeseen environment and kind of is able to finish a goal that is tasked?
Yeah, that's a good question because in the field of quadruped robotics, I'm really impressed by now many labs being able to do quadruped locomotion in structured terrain, plus also navigation. So you just tell the robot go from here to here, and the robot discovers how to climb over obstacles, or sometimes to go around and things like that. So the locomotion navigation skills are getting very, very, very good progress. The things that are still very challenging is, especially for human robots, is locomotion plus interacting with objects. Even a human robot opening a door, something that's completely simple for us, is still not so easy to do because the interaction of forces with the environment are hard, especially if the environment gets a bit complicated and has its own dynamics. That's still complex in level of the control of the mechanical structure, and even in terms of perception. How to know that a door has a degree of freedom and rotating like that, how to know the dynamics of a complex thing that you carry. So that there are still many challenges. And I really hope, and I think that people should take the bio-inspired approach, because our nervous system is meant to handle that. So first of all, our body is meant to have like compliance and softness that's very useful to manipulate and do locomotion. So as long as a robot will be too rigid, we will miss an opportunity to have this compliance, elasticity that animal and human bodies have. And also in terms of control, I think the human control security is very robust because it has multiple layers. And we need to bring that to humanoids. And finally, what's sometimes missing is a bit common sense. So how to have just common sense. Usually you have like specialized robot that can solve one task, but if you give them a bit a different task, they completely fail. So how to generalize and be able to bring what you learn on one topic to another, and then to sequence and switch between these learned skills, that's still, I think, a big challenge.
Right. Professor, you mentioned that biorobotics approach is the way ahead. How important do you think is these interdisciplinary research and collaboration? And can you share some examples of any successful partnerships that you have done, which has enhanced your work?
So maybe just coming to an important topic, I think to say and I think that we learn from animals is the notion of physical intelligence, where the physics, the interaction is as important, if not more than data. So, in the typical AI, everything is data. You need a lot of data, you train, you generalize, everything is data. That's super important. But once you start to interact with the real world, more important than data is experience. How does things feel? How do you interact? How can you manipulate your environment? And that's more than data. That's interaction. And we need to learn from interaction, discover what we can do, what the world is doing. So this notion of physical intelligence is something that's very much inspired from people doing bio-inspired robotics. So I just wanted to put there. I think that's what we need for robotics is physical intelligence in addition to artificial intelligence. Now, what are success stories in biorobotics? One project that I was not involved in, but is a very successful one, is how to make the Rhex robot. So the Rhex robot is a robot that has 6 rotating legs. It was made by a consortium of researchers in the US. At some point, Boston Dynamics was also involved. But it looks like an insect locomotion. It has 6 legs, and it replicated how cockroaches walk over very complex terrains. And they made one of the best robots that could walk in sand, in mud, in water. If you look online, Rhex robot, you find many very impressive locomotion skills. And I think that's kind of one of the most robust robots ever in terms of locomotion. And that was really much a bio-inspired approach. So that's maybe one success stories that come to mind.
Professor, my last question to you. Where do you see the field of robotics heading in the next decade? And what advancements do you anticipate will be most transformative?
Yeah, I think robotics is living a revolution. So we really see it has been a revolution at the industrial level. So robots did incredibly good in control settings to make our cars, our any electronic device is now made by robots. So that has been very successful. And I think now the next challenges will be in 2 directions. One will be to be in outdoors conditions. So the field robotics being in places with mud, sand, rain, snow, unstructured. So that's one axis where we still have many, many things to do. And lots of businesses will go into that direction. And the other is human-robot interaction. Robots that have much closer interaction with humans. The assistive furniture could be one example. Wearable robots, co-worker robots. And there's still a big challenge and exciting research challenges to have this robot-human interaction. So I think these are the 2 axes where robotics will explode and explore many things. And there's still many things to do both in academia and in industry in these 2 axes.
Professor, thanks a lot for taking time and being part of the podcast. Yes, I think biology is the most coolest thing, the way, because you've got millions of years to kind of evolve, and even the single cell organism to us, the kind of things that we do, which we might call simple, is so complex, and if we are truly someday able to kind of imitate that and kind of put it into a synthetic form, I think the world would be fantastic. Obviously, we would need to kind of build in these fail-safe mechanisms. So these robots are safe, because I think in the next few years, there'll be autonomous robots, the autonomous cars, autonomous bots, and And if we can manage to, like, I mean, I think, in the beginning of the conversation, I mentioned about this dragonfly, the aerodynamic of a dragonfly, or the speed of a cheetah. I mean, if all of those, if we can kind of incorporate into a robot, I think the world would be so beautiful. And I think, I mean, it's so cool. I mean, so important to build robot which has utility. And I think, what you mentioned about, these assistive robot, I think it's so cool. I mean, if it goes out there, I think it'll just completely change the society, even this exoskeletons. So more power to you, Professor. Keep on doing what you're doing. And if my listeners, if you like what you see in here, please press the subscribe button. Until next time, see you guys. Bye. Thank you. Thank you, Professor. Really appreciate this. Yeah. Thank you.
Thank you very much. Yeah. Thank you very much for having me. Yeah.